My name is Douglas Goddard. I work at Cisco Systems, and this is about matching or identifying malware with their control flow graphs. A little bit about, about me. All that stuff I just said. I have a computer science degree. I'm working on another right now, and I pretty much just do computers all the time. The presentation, there will be some background knowledge. So if you've worked with Android or if you've worked with control flow graph stuff before, you might be bored for the first 10 minutes. After that, we'll get into graph matching and control flow graph matching, talk about the algorithm I came up with for this tool, we'll talk about the tool, and then some of its applications, which are pretty cool. So, starting off, Android, you might have heard of it. It's a mobile operating system. It is arguably the largest mobile operating system. There's not a huge amount of insecurity in it. So, with that, it's why am I identifying Android malware? It's really easy to work with. The applications come in zips. It's great for proof of concepts. You can pretty much just list all the files in it, pull them out as you would with any zip file. It's Java-based. Java can be decompiled, so you can bring it back to source code. It's easy to reverse. It's just great to work with. There is still a sufficient amount of malware. A lot comes out in China and Russia, where people use third-party markets, not so much in the US, where they have the Google Play Store, which vets their apps pretty well. There's a couple important files. The first I'll talk about is Android Manifest. That has all the permissions in it, and those are what you want to look at to know if it's going to do something malicious. I thought it would actually be a pretty fun game to do, is this a social networking app or malware? But I don't think there's time for that. The tool to extract this is the Android Manifest comes in like a packed binary XML format, so I use APK tool to extract it. It's a nice tool to use if you want to get the Android reversing. Just example, the permissions, send SMS usually subscribes to a paid service. Receive SMS can be a CNC or remote access commands. Install packages and download packages, you're probably going to get some more malware installed. Find location, you can get tracked. Boot completed, it will persist after reboot, and set alarm is usually to delay before, or so a sandbox will time out before it detects the malware. So the next important file, which is much more pertinent to this talk, is classes.dex. So this is where all the code is stored in Android. In Java, the code is compiled into class files, and in Android, all those class files are packaged into the dex file. You can use dex to jar to bring the APK back to a jar, and then you can use all the awesome Java decompiling tools to decompile it and look at it. And here you can just see a listing of all the classes. They're obfuscated, but they were pulled out and from an APK and made into a jar. Other things in the dex file, there's strings, there's class definitions, and there's methods. Methods is what we are interested in. So just a high-level background, if people aren't programmers, a class in object-oriented programming is something that contains methods and data. The methods contain the code, and that's what we want. So bytecode is the code that is read from the Dalvik interpreter. It's called Dalvik on Android. The instruction units are 2 bytes in length, which just means any instruction will be a multiple of 2 bytes, and the opcodes dictate the operation. So we can use dexdump to get a disassembly and pretty much have the offset in the file. The bytecode, which is the bytes that are in the file, breaking that down, you have the opcode, which dictates the instruction, and the arguments to that instruction. This is the offset in instruction units. The code uses this to branch and know where to go from branches, and the human-readable disassembly. So the disassembly is a direct translation from the bytecode. You have the opcode, which in this case is move, and then you have the 2 arguments, v3 and v6. So that would be assigning v6 to v3. If you're not familiar with disassembly, the branch if NEZ is if not equals 0, v3 is the variable you're testing, and if that is not equal to 0, it'll branch to O23A there. There's that in pseudocode. The one after that, if equals 0, v2, is just checking if v2 equals 0. So antivirus is the next basic, and that traditionally detects based on the bytes of the file. So the file hash is the most basic way to do it, and you can also do the section hashes in portable executables. To take a ClamAV signature, we have the MD5 of the file, the size of the file, and the name of the file. If we scan 2,000 samples that I'm using as a test set, we can match 131 of them. So 131 of them have the exact same classes.dex. The next way to do that is based on byte patterns. So we can actually take this offset in the file and the code that is in the file and create another signature with that. So that's the offset in decimal, the code, and we have the signature name, and the 0 just means file type any. If we scan, we'll see the same 131 files because that's pretty specific. There's evasions to that, though. You change 1 byte and you can change the hash of the file, and that signature is not going to detect anymore. The function may move, or you may add some code and those bytes may change. So there's also, if you write a signature based on a string, there's obfuscation and encryption that would easily get around a signature if you can see it. My malware researcher axe to grind, I'm not saying AV is useless. There are much more complex signature formats to use and much more complex ways to do detection, but that's the background. The solution to this is, rather than looking at the bytes themselves, it's to look at what the bytes represent. So we're going to parse those and look at the structure. The structure is more resilient to changes. So instead of looking at a person's DNA, we're going to look at their hair color. So that brings us to control flow graphs. The basic components of control flow graphs, the first one is a basic block, and that is a series of instructions that's going to get executed from top to bottom once it's entered. And only the last instruction may be a branch, and only the first instruction may be the target of a branch. So if we look at this, if you start with the top instruction, you will execute all the way through until you reach the branch. Once you reach the branch, if it is successful, or sorry, if it fails, it'll go on to the next instruction. If it's successful, it'll branch off to another location. This might look more familiar. It's IDA Pro. So the lines coming off of that are branches, and that's the next component to talk about. A branch is an instruction that can redirect out or execution somewhere else in the code. So examples of this are go to, if, switch case sort of statements. If we take disassembly, we can see that we can move all the way through them, but some of the basic blocks will branch off to places not pictured here, and some other ones will branch off to somewhere pictured here. But that's the basis of the control flow graph. So control flow graph, the basic blocks are the vertices, the branches are the edges, and it's a directed graph with loops. So once again, the IDA Pro might be a little bit more familiar. There's two popular ways to represent control flow graphs. The first is an adjacency list, and that's kind of the human-readable format. The next is an adjacency matrix, and that's the more computer-friendly format. If we take a sample control flow graph, we can number the vertices, and the adjacency list pretty much just has vertex 0 is branching to vertices 1 and 2. Vertex 1 is branching to vertex 3. The adjacency matrix is a little bit different. You have an n by n matrix. So this has 5 nodes, and so you have 5 nodes going down the side and 5 nodes going along the top. And you set the bit if there is a branch between 2 of those vertices. So in this case, 0 branches to 1, 1 branches to 2, 2 branches to 3, 1 branches to 3, 2 branches to 3, and 3 branches to 4. And you can't talk about matrices without linear algebra. So these are really useful for graph operations. You can represent the control flow graph as a matrix, and then you can do graph traversals with linear algebra operations. So if you wanted to retrieve the children of node 0, you take a vector and you set that bit in node 0, and just a multiplication of the vector times the matrix will return its children. And that's a one-way traversal. If you wanted to go backwards, normally you would have to store a doubly linked tree, which is no fun to work with. But with this, you can just set the bit of the vertex you want to target, and then you multiply that vector times the transposition of the matrix, and you can retrieve the parents. I think that's a much more efficient way to traverse graphs and deal with them. This field is called spectral graph theory. It's not new, but there's a lot of work to be done in it. It's pretty much taking linear algebra and trying to do useful things on graphs that you couldn't do on such a large scale without the computational power of linear algebra. So now we are at graph matching. The problem that I was facing is, how could I find the signature on the left in the function on the right? So clearly there's a match on the first node. the second, third, fourth, and fifth. It's very easy for humans to find that match. But if you are a computer, there's some ambiguity. The nodes at depth 1 can have 2 options, and the nodes at depth 4, or the node at depth 4 can have 2 options. So keeping track of that is really hard. The term graph isomorphism just means finding a match in graphs. I was going to put a definition here, but that's all it boils down to. You want to match graphs. When you're matching undirected graphs, it's really hard to do. If they have no attributes, there's no place to start, and trying to find that match can be as expensive as factorial time. And our personal computers could probably handle 20 vertices for a factorial time algorithm before they start slowing down a lot. Thankfully, there are simplifications in control flow graphs. There's direction between the edges. There's a defined entry point. And there's a clear way to proceed through the graph. So there's a lot of ways we can bring it closer to tree isomorphism than it is to graph isomorphism. So in tree isomorphism, at each depth, you're going to have 2 to the depth candidates for each node. So at depth 1, you only have 1 candidate. At depth 2, you're going to have 2 candidates for each vertex. In control flow graph isomorphism, you're going to have a variable number of candidates at each depth. So to resolve this and track it, I built something called a candidacy matrix or a candidacy list. And this is an n by m matrix to track which nodes in the function are candidates for which nodes in the signature. So there we have the 5 signature vertexes on the side and the 9 function vertices on the top. So node is considered a candidate for the signature node if it has a sufficient number of incoming and outgoing edges in it. So if we take these ones, for example, signature node 3 and function nodes 3 and 4, they both have sufficient incoming edges, but only function node 4 has sufficient outgoing edges to possibly match this node. So on the candidacy list, we would mark it as a candidate. You also need to check the parents, and once you find a candidate, if its parents are also a candidate, you can then traverse through the graph and kind of do a graph isomorphism by induction. So as you're going through and traversing down with a breadth first search, you can prove that these match. So node 3 here, it matches, or yeah. Once you have the list of candidates, you can make sure that there's a one-to-one matching with something called bipartite matching. Bipartite just means, or a bipartite graph just means it has 2 distinct sets, and a matching is finding a one-to-one mapping between the 2 sets. So if we had a set like that, we would want to make sure that there is a sufficient condition to satisfy those candidates. The algorithm, it has 4 parts. There's a depth list to track where we are, a candidate list to track the candidacy, the signature matrix, and the function matrix to traverse through the graphs. I'll go through it and it'll speed up. The nodes at depth 0, there's only 2 of them, so they both have sufficient, or the function node has sufficient outgoing edges to be a match. Mark it on the candidate list, and there's bipartite matching sufficient. At the next depth, we have to compare it node by node, so signature node 1 and function node 1. Function node 1 does not have sufficient incoming edges to be a match, but function node 2 does have sufficient incoming and outgoing edges to be a match. So we would mark it on the candidate list, we would check its parents and then mark it on the candidate list. We would do the same for signature node 2. We compare it to 1 and 2, and both of those have sufficient incoming edges to match it, and the parent matches 2. So those are both a candidate. There's a reduction step, just because function node 2 can only be, signature node 1 can only be function node 2, so signature node 2 cannot be function node 2. So then we'd perform a bipartite matching, and there's a one-to-one mapping between the 2. Same for 3, sufficient incoming and outgoing edges, and a parent matches. Then you get to nodes 4 and 5. Signature node 5 has 2 candidates with sufficient edges and a matching parent, and signature node 4 has 1 candidate because of the outgoing edge condition. So the one more step you need to do is match previously visited children, because if you try to traverse back through that loop, you end up in infinite loops. So you also do a bipartite matching like you do on the parents on the previously visited children. Mark their candidacy, reduce bipartite matching, and we would then return true because we have reached the end of the signature and we found candidates or matches for each node in it. And that brings us to the tool. I call it CFG Scandroid for Control Flow Graph Scandroid. There are a few design decisions in this, and I warn that this is a tragedy. It ends in Java. About a year ago, I tried to start writing this. I've been chipping away at it, trying to do pieces while I do other work too. So I wanted to retrieve the Android code to generate signatures. And the best way I thought at the time to do that was to write my own Python parser. And that was a horrible idea. It worked, but there was a bug in it, and I got busy, and I didn't want to fix that bug. Python was kind of slow. So when I came back to this project, I wanted something faster, so I grabbed dexdump, which is written in C. It's the Android tool for disassembly. I was like, that must have the code in it. So I use that, and I write a lot of this program with dexdump. But while I'm doing that, I'm learning that I should not be using the control flow graph structure representation that I'm doing, that I should be using linear algebra. And I also find out about this bipartite matching thing, and I don't want to re-implement the algorithm. So I found out that Java had bipartite matching already implemented, a good linear algebra library, and it could retrieve the Android code with the dexlib2. So that's how that got built. Just the build manager Maven, I hadn't used it before, and I think it's pretty cool. It will download dependencies for you and build it so you don't have to worry about your users trying to manage all the dependencies for your project. So in the tool, there are 3 scan modes. There's exact matching, partial matching, subgraph matching. Exact matching can have multiple entry points, and in Android there is only one entry point into the function, but the try-catch statements do not have a clear branch to them, so they're treated as alternate entry points. So you can have a bunch of try-catch statements also matched in this graph matching. The vertex and edge count must be exact. This was a decision, once I tried it, it was the fastest way to do this, so that got put as default. The next mode is partial matching. It is the same thing, but you just have to have less than or equal, or greater than or equal to nodes in the function to enter and try to match. It slows down a bit because you enter more times, but it is still pretty fast. And subgraph matching is the last thing I implemented, and the graph needs to be normalized to only have one entry point. So you strip away all the try-catch blocks, and then you go through and compare that entry point to every node in the target function to see if the signature will match somewhere else in that function. This slows down a lot. It'll take a run up to 20 minutes, but it also has not been optimized yet, so I think there's a lot of shortcuts I could do to bring that back down to a reasonable time like the other scans are. So the signature format is an adjacency list. The name can be anything without a semicolon because that's what I use as a delimiter. You put the vertex count in, and that's an optimization for reading the signatures in rather than parsing the adjacency list and getting the count and then re-adding it. I just use that to allocate the matrix quickly and put everything in there. And then the adjacency list. If we break that out, we can see that 0 branches to 1, 2 in this signature, 1 branches to 3, and 2 branches to 3. Demo time. So have it compiled here. Time Java jar compiles into a jar with all the dependencies. We can see the options. Is that readable? So the basic usage of it is you point to the files you want to scan and the signatures you want to scan with. If you don't have any signatures, it can actually dump them. So let's go with files, samples, Zitmo. So that's Zeus in the mobile. We're going to scan all those and we're going to dump the signatures. I should have just scanned one of those. So, we dump out all the signatures because writing signatures is hard. You can see them, then you can go through and target what you want. You can grep out well-known packages. Normally I would grep out Android, but in this case, one of the malware actually takes on the Android package name to try to trick researchers. So once we have those signatures, I have a few in sigzitmo.adb. I just have two of them. I think these are actually the same signature, but we can then scan with that set of signatures and see a sample output. Tells you the file it's scanning, and then if there is a match, it tells you the signature it matched on and the function that that signature matched. So if we want to stress test it a little, we can do samples, and I have 2,000 samples of what VirusTotal claimed was fake inst, or what AV companies on VirusTotal claimed was fake inst. I have about 6 signatures to scan these with, and I will switch to another tab while this runs. Going through these options, you can change the exact match, or you can normalize the signature if you want to normalize away the control flow graphs. One match only matches on one signature, so once it finds a signature, it breaks out. That's useful if you're scanning something that might have a lot of duplicates in it, which is something I do later on. The partial match option, you can also suppress the matches or the unmatches. So if you match a bunch of files and you want to continue on and try to match the rest, you can get rid of whichever one you want. The statistics at the end, you can suppress those. And when I'm working on signatures, I don't like editing a file, going back and running it, and going and editing the file, so you can pass a signature in straight on the command line. Simple match is the last option. It only matches on the vertex and edge count. It's really prone to FP, but it's going to be the fastest way to do these kind of scans. So if we go back here, there's a bunch of meaningless results up above it that tell you which signatures matched. But we can see that we scanned just about 2,300 samples. In those 2,300 samples, there were 2.7 million functions. And with the 6 signatures I have, they detected 1,800, and I think that's about 81% of the samples just with 6 signatures. That ran in 41 seconds. I've seen runs anywhere between 20 and 50, which I think is pretty reasonable for 2.7 million functions. So let's get back to the slides. The reason why I think that's cool to detect this many with that few signatures is that there's code changes. I pulled this code out of the Zipmo samples, and so this is just the bytecode for the functions. This is another bytecode for the functions, and if I switch back and forth really fast, you can see that some bytes are changing. So if you were to write a signature just with these bytes, you wouldn't detect the changed function. Tried to overlay them too, it didn't come out too well. So that signature, these two functions have the same control flow graph. So despite the byte changes and the variable changes, they still match with the same control flow graph. For reference, that's what this control flow graph looks like. It's really nasty with a bunch of try-catches. I tried to normalize this one, but if you can see, 0 is down in the corner, so when it normalized to two nodes, and I got a bunch of FPs. But I stripped out the long line to the side, and it still matches, and it does an FP. For false positives, I see that about 10 vertices is the limit. If you have less than that, you're probably going to match another graph. If you have more than that, you'll probably not false positive on another function. There are some weaknesses. There are a lot of methods in each APK. That's not something I saw coming. So when I thought of this originally, I thought of it as a virus scanner, and if you're trying to scan 30,000 samples and you're then facing 300 million functions, it blows up pretty quick. The subgraph matching needs some work, and there is an edge case. So to define the edge case, a sibling is a vertex at the same depth as another, and the parent is a vertex that branches to another. So the problem is when a vertex is a parent of its sibling. And graphically, that's this triangle over here. So this signature, the straight line, should match in this graph. But it doesn't because my algorithm treats that 2 at a different depth in each one. I'm trying to find a way to solve this that's not a factorial time at that depth sort of solution. But if you do add that edge, it does detect. So it detects on the more complex condition, which means it's a false negative and not a false positive. And I like those as a malware researcher. And yeah, that's something I want to do some work on. Maybe allow the factorial time thing if there's 2 or 3 nodes, but then skip it if there's not. There's a lot of optimizations that can be made. Most computers have multiple processors now, and I don't take advantage of anything like that. There's a lot of short circuits to get out of the scans earlier, and normalization and subgraph matching can be optimized. So the applications. First is sample or method attribution like we saw. You can use it as a virus scanner. Next is function naming and deobfuscation. A lot of Android malware takes their names and just mangles them to all hell. So you go in there and you have like a.a.a function. And so having this, you could then apply a set of clean signatures or a set of known signatures, and you could say, oh, that a.a.a function is a Google function. I won't write a signature there. The next one, so that's kind of like IDA's flirt signatures. So if you're doing disassembly or reversing, you can quickly identify stuff and know where to focus your efforts. Clustering is what I'll get back to. In binary diffing, I think this algorithm could be used to know where control flow graphs change between two programs. Clustering is what I tried to do last night. So what I did was scan the 2,000 files with all their signatures where the vertex count was more than 10. I used that match once because there were going to be a lot of duplicates in there to get out early, and then I ingested those results into a graph database. So the graph database schema was really simple. One vertex is a file and the other is the signature, and the edge between them is a match. So if we put that into a graph database, we actually get pretty well-defined clusters of this malware. So this was stuff I all downloaded as fake inst, and there's about 10 or so distinct groups within that. So this could be used for strain tracking. To describe this a little, the colored nodes are the signatures. The only way I could add color to them in bulk was as rainbow, so they're all different colors. And the white dots are the files. So you can see at the middle of one of those big clusters, there's a few functions that bring it all together. And there's other ones where there's a lot of functions and just a few samples. So if we then do a graph algorithm to pull these apart, we can just generate signatures for these clusters and cover things in mass. For signature generation, one of the big problems is whitelisting. You need to maintain a database of clean functions. So if you're generating these, you aren't generating a signature on a clean function. But yeah, once you have that, you can just grab the signature that matched and merge the bytes together, wildcards out the ones that are different, and there's your coverage. So this tool is not unavailable. You can just insert dead code with a focus on branching, which is stuff I've seen other things do, but nothing is unavailable, and this is just another approach to identify malware with. So the future work, I'd like to look at x86, patch diffing and vulnerability analysis. Edit distance is a string algorithm to tell how similar strings are and do the edit distance between two graphs. And I think this stuff would lend really well to a piecewise or fuzzy hash, where if you just took the vertex and edge counts for each function, strung those together, it would become unique enough to identify a file. So that's something I'd really like to take a look at. And then other than that, tracking malware strains and improving our coverage. This is available on GitHub, GPL-v2. You can also send me an email. I'm not too active on Twitter. That's also my name on Snapchat if you want pictures of trade secrets and my dog. Code references, the Smalley library was really helpful in this. CERN Colt is the linear algebra library. JGraphT has the bipartite matching code in it. Tools I mentioned, APK tool, DexDump. DexDump is just bundled with Android, so I linked to the source code. And then for the graph stuff at the end, I used Tinkerpop, or the Blueprints API, which is a good way to interface with a graph on top of any database. The two graph databases are Neo4j and Titan. I'd use Neo4j for this, but Titan you should know about it if you want to do graph work. And Cytoscape is what I use to visualize it. It's a biomedical research visualization tool, but it's the best one for larger graphs. Other research in this area, Zynamics, Darren Grimm, they both have binary diffing programs, and those were big inspirations. Silvio Cesar, I don't know if I'm butchering his name, but a lot of his papers were an inspiration, and Ralph Rolls and Thomas Dullian, there's a paper link right there, and that's a pretty interesting paper, identifying control flow graphs on other pieces. So, most of all, thank you guys. Thanks for coming out. I really appreciate the turnout.
So, I see this right in my college engineering of the film. It sounds like this would in order for this to work on mass samples on, for example, on x86 Windows, where we're all playing with malware,
Yeah.
it seems like you would have to fully reverse the sample. You couldn't do this on an x86 like a pathfinder, for example. This would have, you have to go through the deobfuscation, packing it, and basically take it back to either bytecode or assembly code, one of the two.
Correct, but you can automate some of that unpacking. So if while you're running it, anytime like memory is written to and then executed, you can dump that to a file and say, okay, this is more code. The biggest challenge on x86 is you can do crazy stuff like jump into middle of instructions. So parsing those control flow graphs is actually a difficult problem. So that's one of the big hurdles and why I started this on Android.
Right. And I know there are, if you go the other way, if you have, it seems like it would work really well on things like leaked assembly code, where you could run through, when the malware guys get pissed off and leak each other's source code. It seems like that would be a good application of this to be able to apply.
Yeah.
To use that as your base and then apply it against all the known Zeus samples against the Zeus 2 source.
Yeah. So, but yeah, that's an area that I'd like to focus on. And right now, IDA Pro is the thing to parse control flow graphs with. It does it the most comprehensively, but there's a lot of overhead with starting IDA Pro for each sample. So I'm trying to look into other options for parsing those out. Cool.
As far as multi-threading, just a thought is, back in the day, I worked at supercomputing conferences, and MPICH, the MPI libraries, work very well, and I'm pretty sure they've been ported to Java for about 10 years.
Cool.
So you don't actually have to deal with thread sync. It basically handles multi-processing, multi-core, multi-threading, all that for you.
Cool.
But I'm pretty sure there's things in MPICH.
I'll have to check it out.
Yeah.
Cool.
It scales infinitely is why you use it, because it'll go from one processor to 100 with no changes in code.
Well, that's it for me. Sorry for the short talk. Hope it was enjoyable.